Deductive lambda calculus considers what happens when lambda terms are regarded as mathematical expressions. One interpretation of the untyped lambda calculus is as a programming language where evaluation proceeds by performing reductions on an expression until it is in normal form. In this interpretation, if the expression never reduces to normal form, then the program never terminates, and the value is undefined. Considered as a mathematical deductive system, each reduction would not alter the value of the expression. The expression would equal the reduction of the expression. History. Alonzo Church invented the lambda calculus in the 1930s, originally to provide a new and simpler basis for mathematics. However, soon after inventing it, major logic problems were identified with the definition of the lambda abstraction. Haskell-Curry studied evaluative combinatory logic in 1941. Combinatory logic is closely related to lambda calculus. The Kleene-Rosser paradox is an implementation of Richard's paradox in combinatory logic. Combinatory logic is closely related to lambda calculus. Haskell-Curry found that the key step in this paradox could be used to implement the simpler Curry's paradox. Later, the lambda calculus was resurrected as a definition of a programming language. Introduction. Lambda calculus is the model and inspiration for the development of functional programming languages. These languages implement the lambda abstraction, and use it in conjunction with application of functions and types. The use of lambda abstractions, which are then embedded into other mathematical systems, and used as a deductive system, leads to a number of problems, such as Curry's paradox. The problems are related to the definition of the lambda abstraction and the definition and use of functions as the basic type in lambda calculus. This article describes these problems and how they arise. This is not a criticism of pure lambda calculus, and lambda calculus as a pure system is not the primary topic here. The problems arise with the interaction of lambda calculus with other mathematical systems. Being aware of the problems allows them to be avoided in some cases. Terminology. For this discussion, the lambda abstraction is added as an extra operator in mathematics. The usual domains, such as Boolean and real, will be available. Mathematical equality will be applied to these domains. The purpose is to see what problems arise from this definition. Function application will be represented using the lambda calculus syntax, so multiplication will be represented by a dot. Also, for some examples, the let expression will be used. The following table summarizes interpretation of lambda calculus as mathematics. In the mathematical interpretation, lambda terms represent values. Eta and beta reductions are deductive steps that do not alter the values of expressions. Eta reduction as mathematics and eta reduct is defined by, in the mathematical interpretation, taking f to be a variable then, or by letting this definition defines to be the solution for f in the equation. Beta reduction as mathematics a beta reduct is, and as, then. This rule is implied by the instantiation of quantified variables. If, then is the expression y with the quantified variable x instantiated as z. So, as beta reduction is implied from eta reduction, there is no contradiction between the two definitions. Logical inconsistency. From eta reduction, this rule may be interpreted as defining to be the solution of the equation. In defining the solution to the equation in terms of x and y, the definition implicitly assumes that there is one and only function f that satisfies the equation. However, for some equations there may be none or multiple solutions. The definition may be compared with defining by. This is not a valid definition as the equation has two solutions. The proper definition is, an expression in mathematics may represent multiple values if it has free variables. The variables may be existentially quantified. Existential quantification turns an equation into a disjunction of equations, with each variable populated with a single value in each equation. The solution set for n is, for the definition to be valid, there must be only one solution in this solution set. The mathematical definition of function equality is that two functions are equal if they perform the same mapping. So, the left condition is. The next step is to chop this condition up so that the cardinality is tested for each value for any condition. The following result holds. Apply this formula gives, the inner condition only constrains where. So, the structure of why the condition is, where is not a function of, and the cardinality is 1. This leaves only the case where as a function of the may be written. If a condition on is to be formed, then must be in the form of a function of. Call this function as. Then and are related by. The function must use some mechanism to construct from. For this to be true for any, there must be some way of extracting from. Call this function, defined by then and are related by. Plugging the results back in and simplifying gives no solutions starting with. Where z is a Boolean, an equation with no solutions is formed. Then letting n be the identity function, as, then it is not true that. If we go ahead anyway, and then is neither true or false, and as is a Boolean value, then this violates the principle of bivalence. Multiple solutions. Also, it is possible to construct lambda expressions for which there are multiple values in the real number domain, starting with then letting n be the identity function, as, then it is not true that, if we go ahead anyway, and then, having an equation with multiple solutions is not an inconsistency. However, the derivation demonstrated that, for all, then substituting with 2 gives, substituting with -2 gives, then, which is a contradiction, because the values 2 and -2 are defined not equal in the real domain. Intensional versus extensional equality. Another difficulty for the interpretation of lambda calculus as a deductive system is the representation of values as lambda terms, which represent functions. The untyped lambda calculus is implemented by performing reductions on a lambda term, until the term is in normal form. The intentional interpretation of equality is that the reduction of a lambda term to normal form is the value of the lambda term. This interpretation considers the identifier of a lambda expression to be its structure. Two lambda terms are equal if they are alpha convertible. One way to describe this is that extensional equality describes equality of functions, whereas intensional equality describes equality of function implementations. The mathematical definition of function equality is that two functions are equal if they perform the same mapping. The extensional definition of equality is incompatible with the intensional definition. This can be seen in the example below, where applying a mathematical law changes a function to an equivalent function. Yet the intentional interpretation of equality says that the two functions are not equal. This shows the untyped lambda calculus with intentional equality is inconsistent with mathematics as a deductive system. This incompatibility is created by considering lambda terms as values. In typed lambda calculus, this is not a significant problem, because built-in types may be added to carry values that are in a canonical form and have both extensional and intensional equality. Example: in arithmetic, the distributive law implies that, using the church encoding of numerals, the left and right-hand sides may be represented as lambda terms. So the distributive law says that the two functions are equal. The distributive law should apply if the church numerals provided a satisfactory implementation of numbers. Left-hand side, right-hand side, comparison. The two terms beta reduced to similar expressions. Still they are not alpha convertible, so according to intensional equality, the left-hand side and the right-hand side are different functions, and are not equal. But according to the distributive law, the two functions are the same. If the two functions are applied to the same church numerals, they produce the same result, so in that sense the distributive law holds. But the functions themselves are not equal. This is a significant problem because all values in the untyped lambda calculus are terms that define functions. So any mathematically correct transformation of a lambda calculus program may change the meaning of the program. Set theoretic domain. Lambda abstractions are functions of functions. A natural step is to define a domain for the lambda abstraction as a set of all functions. The set of all functions from a domain D to a range R is given by K_in. Then the definition of the set of all functions is given by F_in. This definition is an unsolved equation for F. If there exists no function that may not be applied to itself, then there is a set F that satisfies the above definition of all functions. This is the case with lambda calculus, as there are no restriction on the domain of parameters. However, consider the Church numerals. If the functions on Church numerals, such as plus, minus, times and divide, were restricted so that they only apply to Church numerals, then these are functions that may not be applied to themselves. This restriction is desirable because the Church arithmetic functions do not meaningfully apply to functions other than Church numerals. However, then we get a version of Russell's paradox. See also Rice's theorem, which relates to partial functions. To show this, assume G is a function that may not be applied to itself. Firstly, assume G is in F. This will be used to deduce a falsehood. Instantiate X as G, which is false because. Secondly, assume G not in F. Again, this will be used to deduce a falsehood. Starting with from the definition of all functions of functions, it can be shown that, which is false because we assumed. So G is an element of F and not an element of F. Therefore, if there exists a function that may not be applied to itself, then there is no set F satisfying the above definition of all functions. This result limits what can be done with the set-theoretic approach to lambda calculus, while not actually ruling out the lambda calculus domain. The lambda calculus domain is OK, defined as a set, but any modification to it may cause problems. The usual approach to defining sets of functions is to build a von Neumann universe. However, because the only type in the untyped lambda calculus is the function, it is not clear how to do this. Domain of lambda calculus. The problems with lambda abstraction arose when a domain was imposed on it. If the lambda abstraction is allowed to define the domain, instead of imposing the domain upon the lambda abstraction, these problems no longer appear. Lambda calculus is defined by beta reductions and eta reductions. Interpreting reduction as defining a quality gives an implicit domain for the lambda calculus. The rules are: every lambda abstraction has one value. The beta reduction of a lambda term has the same value. The eta reduction of a lambda term has the same value. Alpha convertible lambda terms are equal. If two lambda terms cannot be shown to be equal, they are not equal. If lambda terms may be reduced to normal form, then the Church-Rosser theorem may be used to show that lambda terms are equal if their normal forms are alpha convertible. If not, then the undecidability of equivalence shows that in general there is no algorithm to determine if two lambda terms are equal. In general, this makes it impossible to know what the distinct elements of the lambda calculus domain are. Example: no solutions to one solution. For example, the equation may be coded with Church encoding and using Curry's Y Combinator as, and the recursion is, which is the first line and will recurse indefinitely. The expression never reduces to normal form. However, every lambda term in the reduction represents the same value. This value is distinct from the encodings for true or false. It is not part of the Boolean domain, but it exists in the lambda calculus domain. Example: multiple solutions to one solution using division and signed numbers. The Y Combinator may be used to define an expression representing a whole number square root. The Church encoding may also be extended further to rational and real numbers, so that a real square root may be defined. The Church-Turing thesis implies that in any computable operator can be represented in lambda calculus. Using such an encoding, using the implementation of divide, then, represents two values in the domain of the signed numbers. If n is not equal to 0, however, it is a lambda expression, so has only one value in the lambda calculus domain. Beta reduction of this lambda term never reaches normal form. However, it represents a value, so a single value in the lambda calculus domain represents two values in the signed number domain.